So the two kidneys are going to be the key organs for the renal system, and so they are found here. We have a left and a right side, and these lie in the back of the abdominal cavity. And so each kidney is supplied with a renal artery and a renal vein. And so the blue here represents the vein, and then the red represents the artery. So the kidneys act as plasma flowing through it to produce urine, and so formed urine drains out into the renal pelvis, and then it will go out to the ureter where it will transcend into the urinary bladder and then be expelled via the urethra out of the body. Okay. All right. So the main functions for the kidneys have this fun acronym for A, wet bed. Okay, so for the A, that signifies an acid-base balance, and it helps to play within our blood, but also the formation of urine is a very important factor for that. The W represents water balance, so this is going to work with lots of different ions, sodium being the predominant one that has a concurrent system. Also for electrolyte balance, so now we're talking about potassium levels as well as hydrogen levels, calcium levels. Those are all included there. Also T for toxin removal, so it's anything that we ingest from our food and drink to any type of pharmacological agents as well. All right, it helps with blood pressure control, so it's going to work then our cardiovascular system and be influenced by different hormones. Also, we'll have production of erythropoietin being produced within the kidneys, very important then for red blood cell formation, and then vitamin D metabolism as well, so that we ensure that we have the proper amount of calcitrol and that circulates within the body so that we have healthy growth and remodeling of the bones throughout our lifetime. The nephron is going to be the functional unit of the kidney, and so there's about 1 million nephrons in each kidney, and this is the smallest unit that can perform all the functions of filtration, reabsorption, and secretion for the kidneys. And so there's two main components that we find with the nephron. We have the vascular component, so this is where we have the interaction with our capillaries and bloodstream, and then the tubular component, which is going to be the site of production for urine. So if we take a look at the vascular component first, so we have, this again has to do with the bloodstream and the vessels. So with the afferent arteriole, this is going to come from the renal artery, and so blood is going to pass through these arterioles where it's going to deliver blood then to this glomerulus. The glomerulus is going to be a ball-like tuft of capillaries where we'll have water and solutes that are going to be filtered through the glomerulus as blood passes through it, and then the filtered fluid then passes through the tubular component, so the production and beginning of the urine production. Okay, so then the blood flow is going to continue out and it'll go to the efferent arteriole, which transports blood from the glomerulus, and then it's going to break down then into these peritubular capillaries that are going to surround the tubular part of the nephron. And then these capillaries are then going to join back into the renal vein, and so now we have the transferring then into the vena cava for our deoxygenated blood now. Okay, so then the tubular component, this is going to be a hollow filled tube that's formed by a single layer of epithelial cells. And so it begins here at this Bowman's capsule, which is going to kind of encompass that glomerulus. Okay, so this is where we'll have the interaction between the vascular component and the tubular component. And so from here we have a nice convolution of this tube, and so it's going to travel from the proximal tubule, and then we'll go into the loop of Henle where we're going to concentrate the urine, and then we're going to travel back out to the distal tubule where we'll have more and more ions that are going to be reabsorbed, and then finally we'll have the collecting duct and then out into the renal pelvis where then it will continue on, make its way out of the body through the kidney. So the structure of the glomerulus is very important because it allows for its function, so that allowing for that physiological properties to ensue. And so the renal corpuscle or glomerular corpuscle is used interchangeably, just to let you know. And so the capillaries of the glomerulus are going to be fenestrated, so that when we look at these, here you see these fenestrations here. And so these are tiny little slits. Here, let me use that color instead, that are found within the glomerulus. And so these allow then for water and solids to leave, but not large items like blood cells or plasma proteins. Okay, so the big thing with these with this structure too is that even though it has these fenestrations, which are these little holes in them, the basement membrane though here that is in between the glomerulus itself and the endothelium, this prevents proteins from escaping, okay, so that we keep that protein within the bloodstream. And the fluid then that enters the glomerular capsule is going to be called filtrate. Okay, and so when we have problems that allow for proteins to pass then through into that tubular component, this is when we have conditions called proteinuria, and so it's just proteins that are found within your urine. And so every time you go in, like when I had my pregnancy screenings, I always had to give a urine sample, and they would always check for protein within the urine because this would be a sign of some type of kidney damage. When we take a look now at this Bowman's capsule or glomerular capsule, again, which is part of the tubular component, and then the glomerulus, which is part of the vascular component, what we have here is a difference in pressure that's exerted from the blood flow. Okay, so at any moment in time, 20% of the plasma is going to enter here, and this is due to hydrostatic pressure of the blood. And again, hydrostatic pressure just means any pressure exerted by a fluid. In this case, we're talking about blood. And so with glomerular filtration, this is now the filtration of the plasma from the glomerulus into the Bowman's capsule. This figure is very important though, because it's showing you that these green dots here are examples of proteins, and proteins are not going to be filtered. Rather, it's going to be other solids, so such as electrolytes, ions, water, those type of materials. Also, blood cells are something that are not going to be filtered as well. And so the filtrate then is what we term as ultrafiltrate. So again, with this filtration, there are no cells, there are no large proteins, okay? And so this is similar to how plasma composition is. So by looking at the volume of fluid that's filtered from the glomerulus to the Bowman's space per unit of time, this is a measure of the glomerular filtration rate. And so this equates to 180 liters per day, which is about 45 gallons per day. And so this is going to be directly proportional to membrane permeability and surface area. So how much glomerular surface area there is available for penetration will affect then the rate of it. And so this can change with contraction or relaxation of the cells that are holding together the glomerular capillaries. Ultimately, this tells us how permeable the glomerular membrane is, and this is determined then by net filtration pressures, permeability of the membranes, and then also surface area available. And most of the filtrate that runs through here is going to be reabsorbed immediately, so between 99 to 99.5%. The GFR is not a fixed value, but it's subject to physiological regulations. And there's two main mechanisms that will control then the GFR, and the first one is autoregulation, and the second one being extrinsic sympathetic control. So the first one with autoregulation, this is to prevent spontaneous changes, and the myogenic mechanism is an intrinsic property that does this on the vascular smooth muscles to contract in responses to stretching forces, whereas the tubuloglomerular feedback, or TGF, is going to be acting as a negative feedback mechanism that's going to utilize information from the distal tubular fluid flow rate to control then the renal blood flow. So we're having crosstalk between our vascular system as well as with our tubular system. Now, extrinsic control, this is now long-term regulation, and so this a lot has to do with arterial blood pressure and ensuing vasoconstriction. And so sympathetic nervous system is going to affect then the afferent arterioles, where it will cause constriction within the kidneys, and then the baroreceptor reflex then will also have innervation with the sympathetic hormones, or will be influenced by parasympathetic hormones as well, such as acetylcholine. Here with these figures, this is now depicting GFR under normal conditions in panel A here. Okay, so what we have then, here is panel A, and we have the afferent arterioles are represented right here. So if we have normal flow going through them, then we'll have normal pressure that's going into the glomerulus, and then we'll have normal flow going out of the glomerulus to the efferent arteriole. And so for the tubule, this results then in normal filtration. All right, so here in panel B, what we have now is vasoconstriction on the afferent arteriole. Okay, so you can see too, here we have a narrowing of that vessel, and so this is going to decrease that blood flow. So the decrease in blood flow then means that there's going to be a decrease in hydrostatic pressure within the glomerulus for those capillaries. Ultimately, what this does then is that since we have a decrease in that flow going from the afferent arteriole to the glomerulus, this is also going to then decrease the GFR, okay, the glomerular filtration rate, because of the decrease in blood flow. So here we have a decrease in GFR. Okay, so this would be an example where we have sympathetic innervation that is causing that vasoconstriction. Okay, another response that would be similar would be dilating the efferent arteriole, where that will also decrease the pressure going into the glomerulus. Okay, then lastly, what we have in panel C here, so this is where we have vasoconstriction of the efferent arteriole. So here you can see decrease in blood flow because we have a smaller vessel now. And so what this does is this is actually going to increase the pressure within the glomerulus. And so this is an example of damming back of blood in the glomerular capillaries. So what this does then is this is actually going to increase GFR because of that increase in pressure. So we're going to have an increase in the amount of filtrate. Okay, so another example of doing this would be to dilate then the afferent arterioles, and that would have a similar effect as well, where we would have an increase in GFR. The steps that are involved then for the renal process or urine production ultimately include these three things now that we are going to divulge into. So the first, the glomerular filtration. So this is where 20% of the plasma that enters the glomerulus is going to be filtered. So we just covered the filtration rate and what can affect it. All right, then the next thing now is going to be tubular reabsorption. And so for this, what we have is that reabsorption is going to be movement of filtered substances from the tubular lumen and into the capillaries. So we're going from the lumen into the capillaries. And then lastly, tubular secretion now. So this is going the opposite direction, where we have movement of non-filtered substances that go from the peritubular capillary into the tubular lumen. And so like a lot of our pharmacological agents, so like if you take ibuprofen, aspirin, like those type of common drugs, then those are going to be secreted out because we don't want to keep those circulating within the body for a long time because we don't need them for vital functioning. All right, so then all three of these processes are going to then create urine. All right, and so that's what will be ultimately eliminated from the body.